Okay, so the recording has started. Now I'll share my screen. So I hope it's visual.
Yes, sir. Visible, sir. Good evening, sir.
Yeah, good evening. So hello everyone. This is week 11 of NPTEL CS52 Reinforcement Learning course by Professor Balaraman Ravindran of Computer Science Department in IIT Madras. I'm Sandarbh Yadav from Computer Science Department in IIT Bombay. And this session is being held on 9th April 2024, which is Tuesday. So again, as usual, the details of the weekly live session, like generally these sessions are on Tuesday, 6 p.m. to 8 p.m. And this is the like second last session. Like after that, we will have one more session for week 12. Like initially, it was planned that we will have a summary session after this week 12 session, but week 12 session itself is on 16th April. And the summary deadline for summary session is like it should be before 18th April. So it won't be possible for me to take a summary session. So what I'll do is I'll summarize maybe the first six lecture today and summarize the next six lecture like in the last lecture week 12 on 16th April. Maybe some other TA like can have a session, summary session. So I'm not sure, like you'll have to confirm with them. Again, the same link and why to attend discussion on practice assignments and assignments, problem solving and doubt clarification, and to ensure two-way communication. So again, the expectation is that you have to watch the weekly lecture videos of uh, week 11 this time and at least made an honest attempt on assignments and practice assignments. Satin and Vato is the basic book. So for lecture 1 to 9, we were following this. But afterwards, since we moved to hierarchical reinforcement learning, we have been following papers. So also like there was a query in the discussion forum that where to get the links of these papers. So I'll discuss them also. And again, as usual, slides and recordings have been made available later. So before that, like I would want to share browser. I'll show like since there are a lot of doubts in the discussion forum that where to find these papers links. So you have to go here, problem solving session recording. I hope you are able to see the browser and then go to this Excel sheet. So in this you can find like this Google Drive folder and in this folder you will find the slides and demos and everything. So suppose for last week, you can go to last week's slides and in the end, like there will be a reading material slide. So in this, you can find the links of the papers. So those papers links are here. Also, like second doubt was like regarding notes or slides. So again, like as I mentioned in one of the initial lecture that you'll have to prepare your own notes. And since the professor is teaching on board, like there are no slides, so those can't be provided to you. Also, like even if someone makes notes, then he makes them according to his convenience. Maybe if he knows some stuff, then he won't write them in notes. So again, like it basically notes depends on like the person itself. So ideally you should have made your own notes. So that is another thing. And one more thing I wanted to ask, so is there like the exam date finalized?
Sir, what did you ask, sir? Once again, sir.
Is the exam date finalized?
Yes, sir. It is there on 21st of this month, sir, Sunday, as
Tw-
per the
21st.
schedule, sir.
Okay, okay.
Yeah,
And
yes, sir. Yes, sir.
it's MCQ based exam, right?
Sir, earlier means from the earlier mails and all, I identified it is MCQ model only, sir.
Okay, okay. And it's offline or online?
Uh, it's online only. In the sense, on computer system, the questions will be there, and we have to attend. No,
Okay, okay,
no,
okay.
that
Right,
is the
right,
method, sir, directly. Yeah.
right, right. And one more question, like, is it like you have to? like do you guys have access of last year papers or something, like to get an idea about like how much time is there and how many questions are there in that time?
Sorry, sir. Actually, how many questions we don't have any idea, but it is for 3 hours, sir. Actually,
Okay,
and
3 hours.
3 hours and 100 marks as usual, and that is the
Right.
process.
So I'm not sure. I also don't have an idea, like because these details are not provided to us. But let's see. Maybe like so.
Actually, we are
Basically,
curious.
yeah. Mhm.
Actually, we are curious to know the question paper pattern and all, sir. Actually, how many questions and all, that I'm not also aware. Actually, sir, I'm also curious to know about that. Thank
Yeah, right. So actually, like I also don't have access to those last year papers. So I also don't know, but maybe like better prepare everything what is there in the syllabus and do well. Yeah. So with that, like I'll move to the guidelines. So generally these guidelines. So first we will start off with practice assignment, then some problem solving, and then demo. Today I'll do a demo of MaxQ, and then finally assignment. So these are the week 11 topics, which are MaxQ value function decomposition, and option discovery. So all these are like, this is the like third framework of hierarchical reinforcement learning. First was options, and second was ham, and these were done in week 10. So practice assignment 11. So the first question says that is true or false. So each subtask MI in the MaxQ framework is not an SMDP. Is it like true or false? It's false, right? It is an SMDP. And why is that? Because like because the actions taken can comprise of the primitive actions also, right? Or also the other non-primitive actions also, like which are subtasks. So you can write subtasks. So in that way, like you can see like it is an SMDP. So it has to be an SMDP. So each subtask MI in a framework is not an SMDP. This is false. So now I'll move to the next question. So recall that the max q value function decomposition, we draw a call graph where nodes are tasks and edges show the dependency of the task. Which of the following is true about the graph? So is it like the graph must be a tree? Is it like, did we see a structure like this? Like something like this was there, but remember this kind of thing can also happen. Suppose we remove this edge. So in tree, like if we have like four nodes, then there must be three edges. But this kind of structure is also possible in this call graph. So it's definitely not a tree. So graph must be a directed acyclic graph. Yeah. So this is the correct answer. You might know already if you have watched the lecture. So it should be a directed acyclic graph. So can it be a any regular graph without self loops? No, not just self loops. You have to avoid cycles also. And this graph, like it needs to be directed also. So again, like this is also wrong. And any directed graph can be a call graph. Not just directed, you have to ensure no cycles and no loops. So basically dead. So this is also wrong. So second is the correct option. So mostly in like last few lectures, like most of the questions are theoretical, not much to do with calculation. But I'm not sure like whether this trend will continue in exams also. So the third question is it true or false? In the MaxQ framework, rewards of the core MDP are not available while learning the policies of the subtask. That is, the agent is responding, agent is restricted to the corresponding subtask pseudo rewards. So basically, like the rewards of the code MDP are available, right? This is all. So this is false. Because like we saw a scenario in which we were having pseudo rewards as zero. In that case, like we were simply relying on the core MDP rewards. So like we have to have access to core MDP rewards. So this statement is false. Maybe I'll check. Yeah. So now the last question of this section. In the MaxQ framework, the expected reward function R bar SA of the SNDP corresponding to subtask MI is equivalent to the projected value function V pi I of AS. Was it like V pi I of AS, or it was just simply V pi of AS? Right? It was this entity, not this entity. So this is simply from the equation in the class. So again, this is also false. So if there is any doubt in any of the four questions, then you can ask now. Otherwise, I'll move to the next one. Okay, so the next section is problem solving. So again, not many problems here. Just a couple of problems in this. Like these problems are neither part of practice assignment nor like the assignment. And I would suggest like better focus on these problems, like problem solving ones, because it might happen like some of the problems from this problem solving sections might be there in your exams. I'm not sure, but could be. So the first question here is using the MaxQ approach leads to solutions which are, so when they say MaxQ approach, like this is by Tom Dykes, right? Like the vanilla MaxQ approach. So remember, like in the lecture, it was discussed that this original MaxQ approach had some issues, which like made it like just recursively optimal. And then eventually, like some other researcher came up with an advanced version of this MaxQ approach, and it became hierarchically optimal also. So currently, like the vanilla approach is just recursively optimal. So MaxQ policy, you might remember, like MaxQ policy of core MDP, MaxQ policy is simply a set of policies, right? Like suppose if there are these subtasks M0, M2, and dot dot dot, suppose M3. So correspondingly, we will have like pi 0 and pi 1 and till pi k. And basically like your job is to like actually solve the each subtask in an optimal manner. And once you solve each subtask in an optimal manner, basically try to find this pi star for this zero task, you will try to find pi star zero. And when you do that, like it's basically the definition of recursively optimal. So if there is no doubt in this question, I'll move to the next question. So the correct answer is recursively optimal. But either way, like there are some variants of this MaxQ approach which make it hierarchically optimal also. So if you are interested, you can read up those also. And the second question in this is each subtask MI is an SMDP. Why? So they are basically asking why each subtask MI is an SMDP. Because first reason they have given is the state space of the subtask is the subset of the state space of the core MDP. Is this the only requirement? We cannot say like if the state space of a subtask is a subset of the state space of the core MDP, then it's an SMDP. This is not the defining characteristic, right? Because you can have a reduced state space and it can still remain an MDP. Another MDP may be a smaller MDP. So you cannot say it's SMDP. So this reason is not the appropriate one. And the second is each subtask has its own policy. So you can divide the task. Suppose if your MDP is not connected, like connected in like very weakly, then you can have each subtask has its own policy. But like again, like this is also not the defining characteristic of an assembly. So this is also wrong. So actions in a subtask can be temporarily extended. So this you might remember from the definition of an SMTP. Like this is a key characteristic of an SMTP. Because temporarily extension means like there might be some time like while you take some action. And remember this tau. So this tau was the waiting time. So this time holding times, some people call it holding time also. So due to this, like maybe some subtasks might take longer time. So this was a random variable at that point, but this is the like defining characteristic. So each subtask is an SMTP because this is the correct option. And fourth option says that the rewards received in subtasks depend not only on the state but also on the subtask in which an action was executed. So again, like this is something which is related to MaxQ, but not like SMTP is something general, right? So again, you can ask this. Because SMTP was defined in last lecture and it can be applied in options also. So I think like this is the last question of this problem solving assignment. If there is like any doubt, you can ask me now. Maybe I'll check those. Okay, so there's no doubt. Now I'll move to this here. Also, just me. So I hope browser is visible to you. So before moving to the demo, I'll review. So in last lecture, like someone asked like to suggest some research topics in reinforcement learning. So basically what I am going to do is give a brief like kind of directions on this. So again, like as usual, like you can have deep RL and like in our course, like we did only DQN, right? Not like there are other algorithms and basic DQN and there's some fitted Q iteration. Some and in that also like these neural networks were not very deep, like simple neural networks were there. So you can try out like different variants of this different algorithms of deep RL. Like I have already referred to you blog by OpenAI. So it has a lot of description about these algorithms. So you can refer that to learn about different deep RL algorithms like PPO or TDPG. So all these algorithms are there. Like based on your interest, you can read up about them. So first is like deep RL. Then HRL, hierarchical RL, like a brief introduction has been given to you in lecture like this 10 and 11. So if you want to pursue this, you can read up more about this hierarchical reinforcement learning, like MaxQ and options and HAM are just the beginning. So afterwards, like there are a lot of papers which came up in this domain also. So you can try out with this one also. And it's still like growing. So you can try out this also. Then there is inverse reinforcement learning. So in which like we kind of try to learn the reward instead of like trying to learn a policy. So you can look into this if you are interested. And there is imitation learning. So imitation learning is basically like learning by imitation, like some expert is there. So you try to imitate that expert. So that is imitation learning. So there are some bugs in this field also. So you can look into this. And then there is a growing field which is multi-agent reinforcement learning. So whatever like we did till now, we had only one agent. Remember, like this was the environment and we have just agent. So our definition was like whatever is outside this agent was the environment, right? And this agent was taking action on this environment and this environment was coming up with reward and next state, right? So this is a single agent framework, but you can have multi-agent framework also in which, so this is the fifth one, multi-agent framework in which like there are many agents, like and these can like interact in a cooperative way also, like they can cooperate towards a goal or even competitive way also. So like small games like you can think like games if you want to model both the players of a chess, then it becomes a multi-agent reinforcement learning with two agents. And if you want to go for like even bigger games like sports, like football. So you'll have to model each player. So there will be maybe 22 agents, excluding the substitute players. So in that field, like you'll have multiple agents and they can be part of the same team or they can be opponents. So sometimes like both objectives are there. They are competing also, but they are cooperating also. So there is a trade-off. So this is another field, multi-agent reinforcement learning, which you can look into. And recently, like there has been a new field like multi-objective reinforcement learning. So as of now, like till now, we have seen only single objective reinforcement learning. Single objective. So basically, our aim was to like maximize the reward, like whatever, like you can think it's a discounted reward or average reward, like different formulations were there, and this is a like accumulated sum. So, but there are cases when you don't want to simply maximize the reward, but minimize something also, like minimize maybe risk factor. So, like risk, sometimes it's modeled as standard deviation or variance. So you want to maximize the reward also, but want stability also. So these are like slightly conflicting objectives. So for that, like multi-objective reinforcement learning is there. So you can look into that also. And then recently, like there is explainable reinforcement learning. So this concept of explainability is coming. So even though like you develop RL algorithms, RL agents, and show them to the agency where you want to deploy. They will ask you like for explanation, like how it's working. Like it should not be a black box kind of thing. You should be able to explain why it's recommending some action. If it's recommending like to go left, what is the intuition behind going left? So you should be able to explain. It should not be just a black box like maybe neural network with state. So you should be able to explain why like some state is maybe getting higher weightage, and due to that combination, this action is getting recommended. So that is explainable reinforcement learning, and this is also our recent area. Then there is reinforcement learning with human feedback. So this you might already have seen in ChatGPT its use. So there is a human in the loop, and it gives feedback to these RL algorithms. So this is another area. So basically, like you can see, and another area like which I missed is bandits. So bandits, although like the course didn't devote much time to bandits itself, like bandits is a special case, but when you look at the like in the research community, like bandits, like there are a lot of papers in bandits. So a lot of research is going on in bandits also, multi-armed bandits, contextual bandits. So you can look in those areas also. And one good thing to do is what you can do is suppose there are popular conferences, right? Like maybe so this is one of the famous conference. You can go to New Reps and maybe like just go to their conference page and it's suppose 2023 is already done. So we'll go to there and you can search for like maybe reinforcement learning. So accordingly, like it will show up some papers, like you can sort them and like there are many papers. So with this, like you can have an idea like what all things are going on in the research area currently. So not just like conferences, like there are various conferences also. So you can look at maybe Neurips is just one of them. Then there is ICML, then there is ICLR, then you can look at triple AI, and there are many others. Like and not just conferences, you can look at journals also. So there are popular journals also. So you can look at these and see like what is happening currently in the reinforcement learning area. And there is a like ACM computing surveys. So where you can find survey papers of reinforcement learning. So if something has come up recently, maybe like you want to have an intro about like maybe multi-objective reinforcement learning or explainable reinforcement learning, you want to find a tutorial. So in this journal, you can find like maybe a 40-50 page paper and it will summarize like what has happened in the last few years in this area. So you can have an idea about that area and decide whether to pursue that area or not. So these are like some of the areas where you can focus on. So this is like mostly theoretical part. And the important part is applications. So reinforcement learning is basically, it has gained popularity because of these applications. So again, like the first application is games itself. So Atari games, chess, so 3D gammon, backgammon, and there are many other games also. Like recently, so the topic of next week is POMDPs, right? Till now, what has happened? We have been dealing with MDPs which are completely observable. Like if we want to observe a state, we have complete information about that state. But sometimes what happens, we don't have complete observability about a MDP. We have only partial observability. So those are known as POMDP, partially observable MDPs. So again, like there are games in which you don't have access to like complete information. Suppose in the game of maybe some card games, so you have access to your own information, right? You know what cards you have, but you don't know like what cards the opponent have. So that portion is not observable to you. So it becomes POMDP kind of problem. And like in the game of chess, it's completely observable because you can see the entire board, right? So like you can see your pieces also, opponent's pieces also. So it is completely observable. But in these cards, you can see your own cards, you can see, but you cannot see the cards of opponent. So in that sense, it becomes partially observable. And also like in chess, there is a partially observable version of chess also. So this is reconnaissance blind chess, in which like you cannot observe the entire board. You are observing a maybe 3 by 3 grid only. So this you can decide which 3 by 3 grid you want to observe, and accordingly that will be revealed to you. So like some research is going on in this area also. So these are like some of the application areas. So first of them is games. If there is any doubt in this, you can ask me. Otherwise, I'll move to other applications also. Okay.
Sir, in the field of autonomous systems, is the RLS being used or what, sir?
Uh, in which one?
Autonomous systems, they say
Yeah,
like
yeah.
car,
Like
autonomous
right. So
car.
that is actually my next application.
Oh, oh, thank you very much, sir. Thank you. Okay.
Yeah. So second is like basically you can go on robotics, like a lot of like robots actually path planning problems and how to like deploy these robots in real environments. Like a lot of RL algorithms are used. So if you want to move into robotics, then RL is a like very nice application in robotics also. And third is like autonomous vehicles. So you guys might know this person, Andrew Ng. So in like I think 2003, he made a helicopter model and he ran it using reinforcement learning algorithms. So although it was a small model, but still like it worked. So you can read his paper about like how to fly a helicopter using reinforcement learning. So all those like autonomous vehicles are there. Like this is also part of drones or helicopters. So there also reinforcement learning is getting used. And then fourth is finance. So in finance also like recently like a lot of agents are getting developed. So like the states could be like prices or indicators and actions could be like buying or selling. So all those kind of applications are there, like trading and portfolio optimization. So there are like applications of reinforcement learning in finance also. Then again, like I don't have much idea about it, but in healthcare also, like there are some applications of reinforcement learning. So there is a paper in this research journal, ACM Computing Survey. So you can read about it, like how RL has been used in healthcare also. So it's mostly in clinical trials. Then six is like NLP, so you already know like ChatGPT, like it use the component of RL with human feedback. So these are like just some of the areas of reinforcement learning, and there could be many more also. Also, like in with respect to bandits, so bandits have their own applications. Maybe first is advertising. So like you remember like these Amazon platforms and maybe Facebook, they recommend you something like advertisements and all. So in the back end, like reinforcement, because in the beginning they don't know you like what to recommend. So they will show you some ads, then maybe you will click them, and on the basis of that, they will get some reward. So in that way, like they will use these bandit algorithms there in advertising. Second could be marketing also, and then recommender systems also. There are these bandit algorithms getting used. So bandits also have their own applications, and like there are a lot of papers in this. So maybe like I'll show you in bandits itself. So here you can see like reinforcement learning around returned around 13,500. But let's see with bandits. See, it's still like very good amount, 4,600 papers. And contextual bandits, stochastic bandits. So a lot of like research is going on in bandits also. So you can look there also. So these are just some of the areas where you can go, and uh, like this is not an exhaustive list. You can find some area which I haven't mentioned. So it's also possible like there might be some other areas also. So basically like the main thing is like you just look at what is happening in the top conferences like UH, ICML, ICLR, AAAI, and there are many other conferences, and even in journals also there are popular journals in like AI. So you can look and just go to their page and search what's happening, and then you will get an idea like where the current research is headed. Okay, then like with this I'll move to the demo. So this week's demo is about MaxQ. So these are just the simple imports, right? So you'll import NumPy, Gem, Matplotlib, and she want to plot time, mornings. And the environment which we have considered is taxi environment. So this environment was already discussed in class, but we'll give you a brief intro again. So this environment is part of the toy text environments, and like again, like the action space is discrete, right? So there are six sections. So like remember like in that call graph which was drawn in class, there were six sections like up, down, left, right, and you can represent it by like north, east, west, south also. And there were two more actions, whether to like pick that passenger or drop that passenger. So these six were primitive actions. So this is your action space. So primitive actions are here, and observation space, like basically you might remember this. Like, so I'll describe these one by one. So this you can see action space. So 0 is for south or down, 1 is for north up. These are the compass directions. East is right, so 2 denotes that, west is left, and 3 denotes it, and then 4 is to pick up the passenger. So once you are on the location of the passenger, you will want to pick up the passenger. So this is that action, primitive action, and drop of the passenger. Okay. So these are the six sections, and the observations space, like you can see, like remember this grid was 5 by 5 grid. So this is actually proposed by Tom Dietrich himself, like in his MaxQ paper. So again, like you can find the link of this paper here also. So this is the paper. So you can search on Google Scholar or even Google, you might find the link directly. So this is the action space, now the observation space. So there are 500 discrete states because like 5 into 5, like since we have 5 into 5 grids, so there are like 25 grids, 25 cells. So first is the like component is the taxi position, then the location of the passenger might be 5. we had like these four pickup points or drop down points, R, G, B, Y, or he can be in the taxi also. So 25 into 5. And we also need to know the destination, right? So 25 into 5 into 4 gives 500. But remember, like sometimes what happens, like there might be blockages in between. So in that case, you'll have to accordingly adjust this 25. It might become 18 if there are like seven blockages. So accordingly, you can adjust this. And the passenger locations are these, like in the taxi is represented by 4 and R is represented by 0, green by 1, white, yellow by 2 and blue by 3. And destinations again 0, 1, 2, 3. And start state, like you can have the episode can start in any random state, right? So out of these 500 states, it could be in any of the states. And then we have the rewards. So in lecture, like it wasn't discussed, it was discussed roughly, but here the exact rewards are given. So every step, like you'll have a negative reward. So this kind of enforces that you do things as soon as possible, because like the agent is getting -1 for each time step it spends. So it wants to do things as quickly as possible. So -1 reward. And you might remember we have seen this in previous examples also. With -1 reward, we can have discount factor as well. So we will actually have discount factor as one, and plus 20 for delivering the passenger. So you have like successfully picked up the passenger from the correct location and successfully dropped off to the like whatever destination he wanted to do. So in that case, you will see a reward of plus 20. And then like -10. -10 you receive when you are executing pickup and drop off actions illegally. This means that suppose if the patient like passenger was at R and you went to pick up him at Y, then it's a wrong action. So in that case, you'll get -10. And if passenger wanted to go to B, but you dropped him at G, in that case also you'll receive a negative reward of -10. And then an action that results in a loop, like, and there are some other actions also, like there could be, you might be moving into a wall, like this has a boundary, right? So suppose if at this point G you are trying to move up and you'll stay there only. So in that case, like there is no explicit reward, but either way, like since you will be spending one more time step here, so -1 due to that. So other like actions which should not be there, like their penalties can be included by this time penalty. And the episode can end if the following happens. Remember, like I have shown you in this gym environments, they also return a done variable. So done means like the episode has terminated. So the episode can terminate in two ways. First is like the passenger drops off the passenger, like the taxi drops off the passenger. So like there will be a passenger at some location. The taxi goes to that location, picks up the passenger, and drops him to his destination. So in that case, like the episode will terminate. And if like the taxi is not able to do this in maybe like then we'll have to have a time-based criteria also, because we don't want to spend a lot of time in the environment. If taxi is not doing something properly, then we want to terminate it. So that length is 200 time steps. So within 200 time steps, if it is able to successfully drop off the passenger, then it will terminate with a positive reward of like plus 20. Otherwise, if you keep on roaming around here and there, then essentially in 200 steps you will incur a reward of -200. And it might happen that in between you might like drop him illegally also, so you can get this -10 also. So again, like these step and reset are the same function. Reset basically returns the start state, and this it basically resets the environment. And step is basically like we pass the action and it will give us the next state and reward. So this we have seen before also. And these are the arguments. So this is the basic description of the environment, and this is how we import it. So I hope like there is no doubt in this environment. Maybe I'll check that once. So there is no doubt in this. So now I'll move to the demo. So again, like this is the agent class. So this is the link of this gem, and you can see it. So you remember like number of primitive actions are 6 already. So if you remember correctly, there was this root. First was root, then there was like one was drop off and one was pick up kind of action. These were like non-primitive actions. Maybe I'll represent non-primitive as first. And there was that navigation, right? And navigation was taking an argument like destination, maybe where you want to go, or maybe represent this by D. And then in this, like there were 4 primitive actions: north, south, east, and west. And in this also, like there were 2 primitive actions. This happens like when you are at the location where the passenger is, and you want to pick up the passenger into the taxi. Then that's the action, primitive actions. Like you are at the location of the passenger and the passenger wants to enter your taxi. So you maybe open the gate and all that action is just primitive action. And here like the opposite. Suppose you are at the destination, or even if you are dropping at him at a like an illegal place, then also either way like you'll get a reward of -10. But and also you'll open the gate and that passenger will get down from the taxi. So these were the 6 primitive actions in total. And there were 4 non-primitive actions, right? This was the route and pickup, drop down, and navigation. So here, like we are having like this is just like one call graph, which was discussed in the class. You can have different call graphs also. So here, like we will be having 2 different navigation module. So one will be navigation to source, basically to the place where the passenger is, and second will be navigation to destination, where he wants to reach. So there will be 2 navigation. So since there are 2 navigations, so both want to go into the same one. So suppose here it won't be like this. Maybe one navigation for source. So this will go to source, and there will be one navigation for destinations. This will go here. So not one common navigation, and each of these will have north, south, east, west, and this again remains the same. So we'll have like 5 non-primitive actions. So that is described here. So for navigate, we have 2 variants: navigate to source and navigate to destination. Obviously, you can combine them. So you can try out this as an extension, and then another non-primitive action is to get passenger, drop passenger. So essentially these nodes, which were named pick up or drop off, because these are non-primitive actions. And the last one is the route. So these 5 are the non-primitive actions. And like since the environment, like this taxi environment provides us with just the primitive actions. So it will give the number of actions as 6 only. So but we need to include these non-primitive actions also. So here it is happening. So our number of actions become like whatever this will return 6 and plus number of non-primitive actions. So that will be 6 plus 5, total 11 action. So this is the agent class here. And the agent class is basically like our agent class of the agent, and it is having an init function. So when you like make an object of this class, it will take parameters like which environment you want to make. And alpha is, as usual, the learning rate, and gamma is the response factor. It will take these 3 arguments and make the object of that class. So this is like happening inside the init function itself. So total number of actions will become this. Either way, like number of states will remain the same. We won't be tweaking with this. And this is a like value function. So remember, like value function, we reverse the notation. So now actions into state, and this is the completion function. So number of actions, number of states, and number of action. So this is a matrix. Like here it's 2D matrix, here it's 3D matrix, and Like these are initialized to 0 in the beginning, and then eventually, like when the updates come, we will update them. And there is a copy also of this field. So numbering of the actions. So you might remember from this one. So for the primitive actions, we will retain the same numbering: 0 south, 1 north, then 2 east, and 3 west. So it's same south, north, east, west. Then pick up like these first six are primitive actions. Then like navigation, for navigation, like it's we'll use go to. So since we are having two kind of navigation, so go to source is defined that sixth action, and go to destination is the seventh action. Like not seventh is actually eight since the indexing is started from 0, but either way, like the index is 6 and 7. And then this is the get and put action. So essentially this one, get and put, non-primitive one. So those are number 8 and number 9. And then finally the root is number 10. So now like this is the call graph which you want to have. So this set is basically an empty set. So remember, like for the primitive actions, so this graph basically represents in each node what are the possible actions which you can take. So in the primitive actions, we don't extend the graph further, right? Graph ends at those primitive actions itself. So we'll have an empty set there. So these six primitive actions will have an empty set. So south, north, east, west, pick up, and drop off. These have an empty set here. Now for go to source and go to destination. These are essentially our navigation ones. So remember, like there we have only one navigation, but since we are going with two navigation, navigation to source, navigation to destination, and each of them will have like this north, south, east, west. So go to source, north, south, east, west, and north, south, east, west. So these are there. And then comes the other two primitive actions. So this one. So either it can have a primitive action, right? So it can have the primitive action of this pickup, get one, and or it can go to source. So it can go to navigate source. And similarly, put can have a primitive action of drop off, which is this action, and or it can go to destination, basically navigating to destination. And finally, the root will have put and get. So this is the call graph structure. Essentially similar to what was discussed in the class, only one difference that for navigation, we are having two different navigation from like different ones for source and destination navigation. Okay. So again, like since this init function came up with alpha and gamma and also environment, we need to initialize those variables also. So these are the class variables. So self alpha becomes alpha. This is the discount factor. R sum is basically like whatever sum any of reward. So initially it will be 0, and as and when we get reward, we will keep on adding it. And we are having this new state also, and then done initially like the done variable will be false, and then like we will when the episode terminates we'll make this loop, and number of actions also 0. This number of actions will be needed because remember in the equation there was gamma raised to power tau. So in order to capture that tau, how much time has elapsed, so that thing is captured in this number of actions. So again, there is one more. So if there is any doubt till now, like you can ask me. Otherwise, I'll move to next function. So next function is primitive. So this basically you give an action to it and it will return whether this action is primitive or not. So remember, like we defined our actions in such a way that the primitive actions are from index 0 to 5. So if it's less than equal to 5, then it will return true. It's primitive, otherwise it will return false. Then comes the is terminal action, the is terminal function. So this will take an action and done variable, and we'll see like whether like the we have reached the terminal state or not. So these are the suppose locations of R, G, B, and Y. So this is like coordinate system 0, 0, 0, 4 is the green one, and 4, 0 is the blue one, and the yellow one is the 4, 3. Then also like what the initial state will provide us is this XC location. So taxi row and taxi column, like these two X and Y coordinate will be sufficient to know the taxi location, and also passenger index and destination index. So the current location of the passenger also and where he wants to go. So these can be like you can get them by decoding this state. And again, this taxi location will be this X coordinate or Y coordinate. And this terminal basically returns whether like we have reached the terminal state or not, if by taking some action. So if done is already there, if done is true, like the episode has terminated, then obviously we can return true. So this will mainly be used if we are in root. So if we are in root and done is there, then we will return true, because it will simply mean that we have gotten to the bottom of the call graph and come back to the root again. And at that point, this done will become true. And then if a equals to self dot root, return done. So if like the action is self dot root. So if we are at root, then we will return done. So here like it was kind of taking if done is true, here we will return done. It can be true also or false, whatever like done is there. If we are at root, so if suppose we have just entered the root, at that point of time, done will be false. So we need to go down. So at that time, it will return false because it is in terminal. But once we have explored the call graph and come back to root again, at that point, done will become true. So then it will return. Then comes the second one. This is put. So put is this one. So again, it's a non-terminal action. So what happens like basically like passenger index. Remember this passenger index can be 0, 1, 2, 3, and 4 means it's within the taxi. So if passenger is at the location, so if action is put and you will return where the whether the passenger is at the location. If it's at the location, then you will return true. Otherwise, you will return false. And this is for put. So put basically means that you are putting the passenger, and get means you are getting the passenger. So I call it formally. So this is put. This is get. So this was pickup. Pickup is getting, and dropping off is like basically putting the passenger. And this is put. So here, like passenger index is less than 4. This basically comes from here. So remember passenger index. Passenger locations can be 0, 1, 2, 3. So it means that it is at one of these places, RGBU and Y, and 4 means it is in taxi. So this basically means that if like you already had the passenger in your car, in your taxi, and you have dropped him off to that location, then it means that your task has ended. And this get means that you reach the location and the passenger is now in your taxi. That point you'll terminate this one. And then elif last this one is go to D. So this is navigating to destination. So here like what you will return is whether the passenger index. So if the passenger is in your taxi and also taxi location is like whatever destination of the passenger was. So here you'll use that primitive and like once you have reached that location and passenger is in your taxi, then you'll initiate the primitive drop off because like you need to reach that location first and then you'll drop the passenger. And here like go navigation to source. So this is like opposite of this one. So you don't have like the passenger is at the square RGB or Y, it's not in the taxi, and you have reached the location of the passenger, then you will execute after this primitive get the passenger inside the taxi. So in that case, like these are like Boolean combinations. So this is basically returning like for each action, like whether you are in the terminal state or not. And obviously for primitive action, you'll always return to this will check whether it's a primitive action. If it's primitive action, because there's nothing more to do after this. Like once you take a primitive action, you go back to this one. And again, like it will maybe it can go upwards also, or it can call some of these actions again. But that would be next situation. So at that point, you will be in terminals. Okay, I'll check. Okay, so There is no doubt. So again, like this is the evaluate function. So these functions are there. So this is simply to evaluate, like you will give the action and state, it will evaluate. If it's primitive action, then it will return the value of that corresponding to that action and state. Otherwise, like if it's not a primitive action, then you will have to actually calculate that value, right? So you will call this evaluate function recursively and pass the this j for each j, and you will basically like select the one which is having the highest value, right? So suppose if you are in this one navigating and you have options of north, south, east or west. So you will try out like north, whether north gives best reward or south or east or west. And accordingly you'll like have the max argument. So this is the max index by arguments, and then you will return that one. There is some kind of Q learning, right? So this is there. And again, like as usual, epsilon greedy has to be there because we need to explore also. So this is the epsilon factor 0.001. Maybe like first I'll like, because these are just function definitions, I'll describe like what hyperparameters we are using, and then I'll come back to this, because otherwise it's simple description of functions only. So alpha learning rate is 0.2, gamma discount factor is 1. Remember I mentioned that since there is a negative reward, so we can have gamma as 1. And it's a like finite task. It has to end because like we have this termination criteria also, right? 200 episode, like 200 length. If it was infinite, then we couldn't have used gamma equal to 1 because there would be issues like the sum total accumulated reward might have gone to infinity. But since this is a terminal, like this is an episodic task of 200 length, so we can use gamma as well. Now, like this is the environment we are getting from Gim, resetting the environment, and this is where like we are creating the object of agent class. And here like we are passing the environment to it, alpha and gamma to it. And this is the training portion, like for J in range episodes. So episodes we are having around 5001. So basically with these hyperparameters, you can play around and see like how things are happening. And this is like for J in range episodes. For each episode, you will reset the environment because like we don't want to continue from where last episode ended. We want to get a fresh start, new start state, and then you will call this max q 0. So this is a function which I'll describe next. So max q 0, it starts from 10th. So 10th is basically the index of root node, right? We need to start from root node. So this is getting passed here, start and root, and this is the state. And whatever reward list we get, we are appending this into this reward, like whatever like taxi awesome, this awesome variable, you know, self dot awesome. We initially set it to 0. So this will eventually keep on getting implemented, and eventually when the episode ends, it will have a sum, and we will put this in reward list. And this reward list then we use for plotting. And for every 1,000 episodes, we are like printing this completed or like completed this many number of episodes. So again, you can play around with more number of episodes also. So now let's go back to this reset function. So first is the reset function and then is the maxq0. Remember like maxq0 is just like without pseudo rewards. So there is actual maxq learning in which pseudo rewards will also come. So this demo doesn't have pseudo rewards. So let's go to reset first and then max user. So reset is simply like this is calling the reset of the environment itself. Like because this is our own definition of the class. This is not from Gym. So in our reset function, we are actually calling the reset, and we want to reset some other variables also. We don't want like the sum of last episode's rewards to be incremented. So we set it to 0. Number of actions also set it to 0. Done will set it to false. Maybe at some point, like then variable might have become true if the episode terminated. So this we want to set it to false again and new state again. So now we go to the maxq function, maxq0 essentially. So here you will be passing the state and the action I. I is the action number, and if self is done, so this is simply to end the recursion. Remember our indices are from 0 to 10, so this 11 will kind of end it. And done is initially false. So if the action is primitive, if we are taking primitive actions, then we will need to update the actual value function, right? Of the core MDP. So we have to make the update there. So here, like we are passing the state, like action, and taking. Remember, this is step function in which we pass the action, and it will return us like this new state and the reward, and whether the episode has terminated or not. And with this reward, we will update the reward sum and number of actions as plus equal to 1. And this is like the update equation, value update equation. You remember, like this one. So new value, so this plus equal basically means like you are adding into the old value. So remember this update, new value is equals to old value plus alpha times alpha is like the learning rate into this is the our reward, this is the target and minus the old value. So same kind of update is happening here. And if the action is not primitive, so again like this, if basically ensures that whatever goes in this elif will be a non-primitive action, because if it was primitive, it would have executed this one and it won't go there. Otherwise, if it's non-primitive actions, then we need to count like how many time steps have passed. Like because we will need that in gamma raised to power tau. So this count will ensure that, and we will do this if until it has reached the terminal, because like here primitive actions like you know like they don't require terminal because they are essentially one step. But non-primitive ones, they will require terminals. So and in this loop, while until you have reached the terminal state, what you will do is you will take the action and according to this greedy action, and then you will have this max q function call itself on this. So and tau. So this is where like recursion is coming in. So because this max q function is calling itself. So this is the recursion. And again, like you will have to evaluate. So this evaluate function we saw, like this is simply used to calculate a target value for our update equation of we need to update this um, completion function also, right? Remember we defined both the value function and the completion function. So it needs to be updated also. So this is the update equation of completion function. So again, similar to this one, a slight difference like that gamma raised to power n will be there. So n is getting returned here. So this will return the count. Basically, we started with 0 and how many times steps it took. So that is getting stored here. This is called in a recursive manner. So that's why it's n here, and then we will increment in the count. And this is the update. So old value of completion function equals to old value of completion function plus learning rate times. This is the target minus the old value. So, but only difference here is gamma raised to power tau. So n is essentially representing tau here, and this is the value evaluate. To evaluate, we are getting this. And in similar manner, we will move to the next step, and this thing will keep on happening again and again. So this is the basic description of this one. If there is any doubt, you can ask me. Otherwise, I'll move to the last part, which is the plotting. So, okay, then I'll move to next part, which is the plotting. So I'll show you the graph basically. So this is how, remember like it's learning in an environment which is giving negative -1 at each time step also. And also like -10 if it's delivering the passenger in an illegal manner. So initially, like the rewards will be highly negative. Like the agent doesn't know like what to do, so it will essentially keep on doing things badly. But as and when like these episodes keep on getting passed, this reward will become less and less. Less in the sense that it's becoming more positive. So we are moving towards 0. Because this is an environment where like you can get above 0 if you like drop the passenger as quickly as possible, like in less than 10, 20 steps. So in that case, you can get a plus reward also because this plus 20 is there. So due to this plus 20, if you drop in within like less than 20 steps, then you'll get a positive reward. But mostly like we want to go close to 0. And this is what's happening with the training. So as and when like we keep on increasing the episode numbers, this training is like now, like we started off with around minus 350, and really we are getting to minus 25, right? The agent is gradually getting better. And at this point, you can see like most of the times it's above zero also. So it has learned well. So this is like max Q0 without pseudo rewards, but you can try out. So basically, like these are the further experiments which you can try out. You can try out different hyperparameters. Like remember these hyperparameters were there gamma, alpha. So these are like just set as values. Like discount factor, you can try out different kind of discount factor also. Like maybe you can try 0.99 something, or alpha lend rate you can play around with and see like how the convergence. Maybe like here like to reach above zero, it may be started reaching at this point. Maybe with some other hyperparameter values, it can go above zero at this point. So those you can try out. And then again, like we had a fixed epsilon greedy policy. So you can decay epsilon and use softmax also. Then you can try different variants of taxis and different environments also. This taxi is just one of the environment. So it was proposed by Tom, and you can try out different environments also. And again, like this is max Q0, so you can try out max Q learning with pseudo rewards. So there's things will be slightly complex, but first you can read it from the paper, max Q paper about this, and you can try to implement this. Also, like since this is like just one of the framework for options and ham, you can try on your own. Maybe like I'll see like if I can get something for options and ham in the next lecture. Otherwise, like maybe I'll focus on probabilities. So these are the further experiments for you. So if there is any doubt in this, you can ask me. Otherwise, I'll simply share this with you. Okay, so with that, I'll move to the slides again. So I hope the slides are visible now, right? So next few demo done. Yeah. So are the slides visible? Maybe someone can confirm.
Yes, sir. Yes, sir. Visible, sir.
Okay. 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 So now we'll move to the assignment level. So again, like this assignment, I won't give you the exact answers, but I'll guide you through to the answers. And uh, depending on like how quickly we finish this assignment, I'll give you a brief overview of uh, week maybe 1 to 6. So essentially, like we are not going to have a summary section after week 12. So our week 12 is on 16th April itself. Also, you guys will also need some time to prepare yourself, and like deadline is before 18th April. So on 17th and 18th, I am either way busy. So maybe some other TM might be organizing a summary session, so you can attend that. So the first question is, which of the following option is correct for the subtask terminations in the MaxQ framework? So is the termination stochastic or deterministic? So remember in options framework, there was this beta in which like with some probability you can terminate, with like some probability, other remaining probability you won't terminate. But here, like in MaxQ, was there some concept like stochastic or something? There was something like either like you will be states in states within that subtask, or whatever outside is simply terminal states for you, right? And the union of this was equals to the set of states of the code entity. So there was no concept of stochasticity, right? So the termination was deterministic. Suppose in the car taxi car example only, if you are in a state which is not part of that subtask, suppose in navigation to something, and you are in a state which is not part of that navigation subtask, then essentially it means you have terminated. So this is what we used in is terminal also function. So with this you can get the answer. So second question says that in MaxQ learning, we have a collection of SMDPs. Okay. In the conventional value function, the only argument was state. Remember, like traditional RL, it was just value of the state. In MaxQ value function decomposition, we have value function of the form b pi of I, comma s here. So where pi is the policy, s is the current state. Okay, so this is simple. What is I supposed to be in the our notebook? Is it like the number of times we have visited this state as? Definitely, this is not correct. So it means it is the ith equation of updates. Again, like this is wrong. So I was something like related to subtask identity, right? So I is the so based on that you can get the answer whether it's C or D. So but first two are definitely not there. So I essentially did some index of the action. And here like action can be subtask also, right? So again, like this description is common to question 3 to 6. So again, this is the taxi problem 5 by 5 grid. So don't think like this is a like two cells. It's one cell only. I'm not sure why the shape is not perfect. Essentially, like these are like 25 cells. The gray colored cells are inaccessible cells or can be thought of obstacles. So we cannot go in these gray cells. So if you want to move from green to blue, then you will go this way. And the corner cells marked as RGBUI are the allow pickup drop points for passengers. So these are the places where passenger will be. So this is the usual taxi example, which we have already seen a demo also. So I think there is something in chat. Say the following is the call graph for the above textual problem. So this is the call graph which was discussed in class. In our demo, we had two different navigate functions, but here again we are back to single navigate function. So these red ones are our primitive actions up, down, left, right, or you can have like south, north, south, east, west. And this is like primitive action. Once you have like reached the location of the passenger, then you want to get him into the taxi. This is that pickup. And once you have reached the destination or you are dropping him off at some other location also, you'll open the gate and do something so that the passenger gets out. It is put down the action. These are primitive actions. And again, these are non-primitive actions. So here we have four non-primitive actions. Right? This is a root node, then pickup. Pickup can either like pick up actually like when you are at that location, you can pick up. Otherwise, you will navigate to that location first. And here drop off. If you have reached a destination or even if you are dropping him at some other location, first you need to reach that location and eventually when you reach that location, then you will come down. And this navigation will basically do up, down, left and right. And again, this everything starts at the root. So this is the usual taxi example. And on the basis of that, we will be solving question 3 to 6. Okay, so the third question is from the below list of actions, which among them are primitive actions? So again, like I have shown you in this one graph itself, like the primitive actions are the right actions, right? You can essentially see like which one. So left is a primitive action. Top maybe it is not a is put down a primitive action. So remember like the name put down is a primitive action. So names might be similar, like this pickup and this pickup might be similar. So you have to be careful about exact names. So again, like pull down is a primitive action, right? But drop off is not a primitive action. Drop off is a non-primitive action. Yeah. On the basis of that, you can get the answer which among these are primitive actions. This is like quite simple one. And just if you have attended the lecture, you can answer these questions easily. So from the discussion in class, it is said that navigate is not a single subtask. Yes. So it has a parameter t in navigate t. So what does this parameter t mean? So is it like the number of times pick up or drop off have called subtask navigate? Again, this is wrong, right? The maximum number of primitive actions permitted to finish subtask. No, there was no such requirement, right? So, or the destination. Was it the destination? So, yeah, it was essentially the destination. Here, like, destination can be viewed in two ways. Like, suppose this is corresponding to the point of view of taxi. So, when he is going to pick up the passenger, destination will be, for him, destination will be source, right? And if when he has picked up and he wants to drop, then destination will become the actual destination. So, here, like, in that sense, you have to think whether it is this one or none of the other. So you can get the answer from this. Okay, so if there is no doubt, I'll move to the next question. Again, based on the same continuing question. So true or false? The ordering of the call graph is important and subtasks should be performed via these orderings. Is it true or false? So remember, like in the lecture also, it was mentioned that do not focus much on this order of the call graph. It's not like that you have to execute up first, then down, then left, and then eventually right. There was no like traversal like this. You don't have to traverse like in this way. You can like do down before up. So that ordering doesn't matter much, right? So on the basis of that, you can get the answer of this one. And here 6-1. So suppose the passenger is always either inside the taxi or at one of the four pickup locations. So essentially this means that the passenger location number is equals to 5. So four location like these RGB or Y or inside the taxi as well. This means that okay, they have mentioned this. This means that there are 5 states for passenger location. Then for the given taxi one, what is the number of states that suffices to define all information? So remember we already saw this in demo. So 25 into 5 and 4 destination. It was this. So which came out to be 500, right? But this 25 was like completely unblocked one. But here it is given that how many are blocked? 1, 2, 3, 4, 5, 6, 7 are blocked. So 7 blocked means you'll need to remove those blocked states because you'll never be in that state. Your taxi won't be in that state. So essentially you'll have to minus 7 from this 25 and then multiply. So in that way you'll get answer. So now like we are outside that question. So this is general question. So state true or false. Bottlenecks are useful surrogative measures for option discovery. Remember this bottleneck. So suppose if some pathway is there like this. So this is known as some kind of bottleneck. So we have already discussed in class, like bottlenecks are actually used as a surrogate measure for option discovery. So we will see like at what point like this is there and we will kind of decide this to be one option. So it is actually true, right? Now, which of the following can be considered as a good option in hierarchical order? So again, like I'll mention again, circle means single option correct. So since exam is in MCQ format, so you should remember this single option correct and this is multi-option correct. Although like in multi-option correct also, it might be possible that only one of them is correct. And generally like multi-option correct means more than one option correct. So which of the following can be considered as a good option in hierarchical order? So what are the properties of a good option? So option that can be reused often, yeah, like this is a good option, right? Reusability is one of the desirable criteria. And option that can cut down exploration. Yeah, this is also one of the criteria. Like we want to have options which will limit our exploration. We don't want to explore too much also. And an option that helps in transfer learning, right? So suppose you have learned to walk, then you can transfer this, like whether you are walking to library or walking to school or you are walking to anywhere else. Like once you have learned this option, then you can use it anywhere else. So this is kind of transfer learning. You are transferring to suppose walk to school task, and you have learned walk to this option, walk at home. So you can transfer this learning. So again, it helps in transfer learning also, like since the three are correct. So these are the three desirable properties of the options. And again, like this is also discussed in the lecture. Now the ninth question. So we define the action value for max q as q pi isa is equals to v pi as. So this is the value function, and this is the completion function, where q pi isa can be interpreted as expected return when you are in subtask I and state S and you decide to perform subtask A. So you are in some state S and you are in subtask I, and now you are deciding to perform this subtask A. So whatever like expected return you get, this is denoted by Q. And this will be like something what you get while performing that subtask A and something which you get after performing, after you have finished that subtask A, right? So this is the completion function. So assume that in taking A, you get reward R1. So this is the reward corresponding to this one, R1. And after completion of A, you get reward R2 in completing subtask I. So this is the reward R2. So basically, this is they are saying that V pi of AS is equals to R1 and C pi of ISA is equals to R2. So, okay. So choose the correct value of Q C pi ISA. So remember one mistake some people can make, they will think that value of q pi ISA is R. So you might write R1 plus R2. But they have asked what is the value of C pi ISA. This is a simple definition based. So if you knew the what this term meant, so this was after the completion, right? So it's essentially R2. So this way you can get the answer of this one also. So is there any doubt in any of these? Otherwise, I'll move to the last question. Okay, so I'll move to the last question of assignment. So in the MaxQ approach to solving a problem, suppose that subtask Mi invokes subtask Mj. Okay, do the pseudo rewards of Mj have any effect on the subtask Mi? So Mi is some subtask and it's invoking Mj. So it's calling Mj. So the question they are asking, do the pseudo rewards of Mj have an effect on Mi? Although they might not have a direct effect is not there, but there could be an indirect effect, right? How? Suppose policy is some policy will be learned for this task, subtask, right? Maybe call it PyJ. And this is learned using like pseudo rewards. Although like, lecture also in demo also, we didn't consider pseudo rewards. We only did max Q0. But like this is concerning general max QQ learning. So there will be pseudo rewards. So this policy will be learned like apart from core MDP rewards, it will be learned using pseudo rewards also. So this pseudo rewards will essentially have an influence on this policy, right, PyJ, which is in this task. And this policy will then have an impact on MI. So although pseudo rewards directly don't have an impact on MI, but through this policy, they can have an impact on MI. So in this way, like there can be indirect impact. Okay. So please repeat Q9. Okay. So question 9 is simple definition based. So remember this equation. So this QISA basically is the expected return when you are in subtask time. So suppose maybe take some example. You are in subtask I and then you call some subtask A. But like you have called this subtask A, you are in some state S But after calling this subtask A, it's not necessary that after A has finished, I will finish also. I might be doing some primitive actions afterwards also, right? Maybe some action A dash and some action A double dash. So in this also, like, it will get some reward, right? So this is like essentially B pi of AS, and the sum will be C pi of IS. So like, you are in subtask I in some state S, you have called this subtask A, but essentially like finishing of A won't mean that you are finishing I also. So whatever you collected while executing A is this, but whatever you collected reward, total reward is after like this A has finished. But you are doing some other things also. You can call some other subtask also, like, or you can call some primitive actions also. So all that reward which you get by that is this C pi IS. So this they have already given that this is R2 and this thing is R1. So they are asking choose the correct value of C pi of IS. So that will be R2. So I hope you got this. If there is any doubt, you can ask me. Yeah, okay. So fine, like with that, all the questions of assignments are done. So again, uh, like someone was asking in discussion forum that the links of the papers haven't been provided, but they are there. Like I think like some people haven't been attending these live sessions nor watching the recordings, so they might not know, but the links of papers are already there in reading material. So this is the paper. Like this is the journal paper which professor was talking about, like which at least you should read once. So here you will get the concept of pseudo rewards and everything. Also like some very good like introduction to SMDP, MDP. So if you want to revise some concepts, you can revise it using this paper. So they have this taxi example also in description. So this taxi example was like described first in this paper, and then eventually gym environment also came up. Use this. So we already saw that. And then there is this library. Okay, so I think like in between I didn't share browser. Just a minute, I'll share browser. Okay, I hope it's visible now. So this was the paper which I was talking about. So this is the MaxQ paper. Once you click that link, you will get it here. And here, like you can read about all this MaxQ, not just MaxQ, but they'll provide you a good introduction on RL, MDP, SMDP, and even this taxi environment, all those equations. If you want a quick summary, like this is how Q pi is defined, Q star, P star, V pi, Wellman equations, and everything. So you'll get it here. And then reinforcement learning algorithms, SASA, and all those greedy in the limit, infinite exploration. I'm not sure whether this was covered, but this is that taxi domain. Then max Q value function decomposition. You can read this paper. It's very nicely written. And again, like just same example is there. And some pseudocode also. So you can read this. Okay. And this is the second link which I mentioned. Like I was mentioning in like few further research areas also. Like these like after these three frameworks, some more like recent algorithms also came up. Like which weren't discussed, so you can find them here. Like this is a library like similar to stable baselines, but this is for hierarchical reinforcement learning algorithms. And whatever like you can find like some environments and some algorithms also here, like and using this different neural networks, goal condition, the HRL. There is this popular one, HIRO, so data efficient hierarchical reinforcement learning, because like whatever was discussed wasn't discussed with regard to deep reinforcement learning. So all these like how to use less data and still get good results. So all those very good things are there, and HAC. So you can find even the links of papers. in the references at the end, and different hierarchical reinforcement learning papers and algorithms are here. Remember this multi-agent DDPG. So this is a library for that one. If you are interested, you can explore this also. So okay. So with that, like our today's session has come to an end. Now I'll go back to the slides. So like, but before like it's 7:30, like I wanted to conduct a brief overview of week 1 to 6. So now we will start that. So this is the like reading material. And thank you. So with this, like our today's week 11 content is over, but I'll be revising like whatever we covered in week 1 to 6. So if you want to stay, like you can stay. Otherwise, either way, I am doing it. So it will be recorded. Okay, just a minute. I'll start with this one. Okay, I'll share the browser again. So let's start with ML itself. So machine learning is basically learning from data. Then there is supervised learning, unsupervised learning, and there is reinforcement learning. So supervised learning, you will get like the feature vector also the label. Here in unsupervised, you'll get just the feature vector, not the label. So here like we will do clustering kind of thing. And here we will do supervised learning, like which if you are doing in discrete space, it will be classification. Otherwise, if you are doing in continuous space, it will be regression. But RL is something special, which is learning by reward and punishment. And it has a specific structure, basically used for sequential decision making. So over time, like there is a time going from maybe t to t plus 1, t plus 2, and in similar manner t plus capital T. So at every time step you need to take a decision. So basically the agent will take some action, and on the basis of that like some environment will be there, and the environment will come up with the next state and the reward, and the underlying structure in reinforcement learning is an MDP, and MDP is basically Markov decision process. And the components of this is set of states, set of actions, then the transition function, then the reward function, and the discount factor. So these five are the key components of Markov decision processes. And like then there are two settings. First is like control. Like there was a like you remember those algorithms, policy iteration, also value iteration. So for all these, like we also saw some demo also. And then there is actual control algorithms, which is Q learning and SASA and expected SASA. And so basically like what happens in this, so these algorithms are under planning domain. So in planning domain, like you have access to this transition function also and reward also. So basically, you know the entire MDP, and your goal is to solve this MDP to reach the optimal solution. Then there we saw like Bellman equations and Bellman optimality operator, and how like applying that Bellman optimality operator again and again led us to a solution, which that algorithm was known as value iteration. Then we saw policy iteration also. And but in like this learning setting, actual learning, it is also called as control. So here we don't have access to this transition function and reward function. So we kind of learn by interacting with the environment. So here it's like essentially computational problem. So we can solve it just we don't want to learn here. We are given the MDP. We just want to find the what is the best solution for this MDP. So that is planning setting, and this is the learning setting. So here, like we don't know the transition function and the reward function, so we kind of interact with the environment and learn. And eventually, like we hope that by like interacting in a like large number of times, like we learn in a good manner. There are convergence results and all, like but you need to ensure some conditions, like you should explore enough, and all those different exploration strategies were also there. So now I'll do is I'll one by one I'll describe like what was discussed in each week. So in week one, so week one, like simply introduced what was the RL framework, like applications of RL, introduction to RL, basically history, like how this RL came up. You might remember the cycle example, introduction to RL, then there was RL framework also, and some discussion on applications of RL. So also like we saw in today's one section where I was discussing the like potential application areas of RL in potential research areas. So there we mentioned some applications, but some more applications like especially in games like Atari and cycling and like remember that example of New Zealand, there were cows and all. So all those examples were discussed here. And there was concept of immediate rewards, which are like instantaneous rewards and delayed rewards also. So delayed rewards are something which we get after some time. So we might take some action. Suppose you in the game of chess, you might make a good move now, but that move might be rewarded at a time step later, not the exactly after you made the move. Maybe it didn't result in checkmate at that point, but eventually after two, three steps, it was so good move that it eventually led to checkmate. So the rewards might come in a delayed manner, and we have this gamma discounting factor, which kind of discounts that reward. So this we can use according to the problem. Then there was introduction to immediate RL, and initially like we spent some weeks on bandits, right? So bandits are basically stateless MDP. And stateless in the sense there is only one state, and like you are taking action again and again. So I think there is something in chat. Okay, yeah, yeah, sure. No issue. So, so these were bandit setting. And then in bandits, like we started off with multi-armed bandit, in which like there will be multiple arms, and we need to pull some arm. Eventually, this arm got converted to action when we reached full RL. So bandit optimalities were there, and there like we discussed three different type of correctness. Like one was asymptotic correctness, like how would we do at infinite something, and the one was regret optimality, like we want to minimize the regret, and there was pack optimality, which was probably approximately correct. So you can remember these three. Maybe there might be something about this on in exam. So probably approximately correct, there was an equation, right? So all those equations you should remember. Then we discuss some value function based methods, and like initially we discussed on a small scale of bandit scale, but eventually we discussed on a full RL scale also. So we did also discuss some abstract like exploration strategy, abstract greedy, and then there was the softmax. So there might be some small calculations on these. And in this, like we also discussed whether to decay them. In stationary environments, you can decay them. In non-stationary, it's better to have a constant epsilon. So all those like things you can, but there might be small MCQs here and there over these. So then in week two, we started off with actual bandit algorithms. So also in like week one, we saw a demo, like you might remember this demo of coin. So here, like we were based on our intuition, we were maintaining, we were having three coins and we were having this tossing this coin, and on the basis of that, how many heads and tails were coming, we were seeing like which coin to pull next, and eventually saw like whether our regret was minimized, and these coins were biased coins. So it's not necessary that they have zero 0.5 probability of head and zero 0.5 probability of tail. So but then we moved to UCB algorithm first. So also UCB, also we saw a demo in which we saw the beauty of UCB algorithm, in which we didn't have to explicitly say that which coin to pull. This UCB came up with that value, like it automatically determined like which coin to toss next. And there was this formula of this, like there was this and there was second term also, right? 2 ln of n and upon number of arms, number of times that arm was pulled. So either way, like if you don't pull some arm nj, this is nj. So if you don't pull some arm, then this term, due to this term, due to this term, like it will keep on increasing, and because this is the total number of tosses, and this is like the number of times you have tossed. So based on that, if you didn't pull somehow some didn't toss some point, then eventually like UCB value was gradually increasing. This we have seen on demo also, and eventually you will be kind of forced to pull that action. So we selected action with the best UCB value. I think there is something in chat. Okay. So this was just one of the algorithm. So although we didn't discuss this, but there is something called KLUCV. You can look at it. There is not from the point of view of exam because it isn't taught. But if you want to learn more, you can see this KLUCV algorithm also. Then there were discussion on concentration bounds. So you might remember Hopton inequality. All those inequalities were there. There might be small questions here and there about these uh, Chernoff opening bonds. So you can be given some like how many times you need to toss so that like the probability of deviation is this much only. So all those kind of small questions you should be able to do. Like basically like the goal is to you should remember those equations. So in this exam, like are they allowing some kind of notes or something in the exam, or is it like closed book?
Sir, it's closed book only, sir. It's closed book only.
Oh, if it's closed book, then obviously you need to remember these equations. So better like go through them like maybe 2 3 times, then
Yes, sir.
you'll remember them.
Yes, sir.
And then like we had this UCV1 theorem also. Look at its proof. So it was a long proof, so you can look at that proof. And just kind of established some bound which was given by Lie and Robbins. So Lie and Robbins, like they give a tightest bound, but this was not the tightest one, UCV one. KL actually achieves this tightest one to the constants also. So that you can see. Then there was some discussion on peg bounds also. And in peg bounds, we discussed some algorithm. First was naive algorithm. So this was not that special one, but either way, like have a look at this also. Then there was median elimination, in which like in every round we were eliminating whatever arms were below the median. So all those you can look at those algorithm, median algorithm also, and there were some associated theorems and lemmas. So better read them. So this is a brief review. Like it's not like I am discussing the topics themselves, just to remind like what all has been covered. Because generally like people forget. And then there was discussion on Thompson sampling. So for Thompson sampling, also like we saw a demo. I think for median sampling we didn't do demo for this spec mounts, but for UCB and Thompson sampling we did demo. and where we use beta distribution. So, but I told you like you can use another distribution also. So based on this, like there might be questions on distribution, like how to do sampling. So here, like we were actually like sampling from a distribution and taking that, not the mean, not just the mean, but the sample from distribution. So it is also known as posterior sampling, and this is quite a old one. This came around 1930s something. So it has been there for a long time. And essentially, like this was week two. Now I'll describe week three. So week three, we started with some discussion on policy side, like how we can, like this was in bandit setting, but eventually, like both for both value and policy, we'll do the recap in full RL also. So basically, what happens if you are using value function, then it's a two-step process. First, you learn value function and then you map it to policy, some using some arguments or something. And in policy-based methods, you directly learn the state to action. Here you learn some state to first real value, and then based on that, you take some arguments or something, and you get the best action. So it's a two-step process. Although like there are many results in theory which says that value function based methods don't work well, but in practice they have been found to work well. Is one prime example is DQN itself. So that was one of the topic in week three. Then we discussed this special algorithm which is called reinforce. So this reinforce has a full form also. I forgot what was its full form, but it has a full form. So this is a special case of policy algorithm, and it uses gradients. So all those equations. So here it was discussed in bandit setting, but again, like we discussed it again in full RL setting also, this reinforced algorithm, and it is one of the most popular policy gradient algorithm. But the issue with this reinforcement algorithm is its high variance. Variance is very high. So eventually, like you might remember, we introduced something like baselines subtraction. So we were subtracting this baseline, and when this baseline was the value function itself, it became active gradient. And so you should remember those reinforce equations. And eventually, like final topic of this week was contextual vendors. So you might remember we did a demo of contextual vendors also in something called ads. So this I remember I did on Kaggle, not on Collab, because some files needed to be stored. So although like demos won't be part of your exam, but just to mention that we tried this also. So click through right one we have done. And now I think like week three is done. So I'll move to week four. So what happened in also in week three, like before moving to week four, we also introduced full RL. So here, like you were given introduction to MDP, what is MDP is, it delayed rewards, immediate RL, and also multi-criteria RL, multi-agent RL, returns. So basic definitions were introduced, like returns, value functions. So all these like you should remember, like what these means, value function and policy, MDP, and like what are the variants? Like there could be it could be Marco, what Marco means, what non-Marco means, and stationary. Stationary means like something which doesn't change with time. Non-stationary means something which changes with time. And you should also remember uh, deterministic. Deterministic means like there is no probability distribution associated stochastic policies. Like basically, if its mapping is a state to action one action, and it's deterministic if it's like probability distribution, so it's a stochastic policy. Remember, in one of the demo, we actually used the deterministic policy, and in that, like, we didn't use exploration because this not deterministic, this is stochastic policy. So in that stochastic policy, like, remember this neural network was there. We, and the last layer we were doing some soft maths, and we were sampling from that distribution. Ideally, like, we could have chosen to go with the action which has the maximum probability, but we were actually sampling from that distribution. So that makes the policy stochastic. So you should remember all these terms, what these terms means. Also returns, like what is like return, discounted return. Then, okay, so finally we went to MDP before MDP modeling. So there was a like rigorous example, like how to model an MDP. You maybe if you have time, you can go through that example again. So low high example was there. And then the main part of planning came up, which is the Bellman equation. So you should remember all these Bellman equations because either way, like, there could be, we have already saw in assignments and all, like, you could be asked to solve these Bellman equations. So essentially, you should know how to solve linear equations also. So linear equation, this will reduce to linear equation and equation and variables. So obviously, like, they won't go beyond three variables. Even if they go beyond three variables, there might be a simple trick which will reduce it to some easy solution. So you should know how to solve these linear equations because this is what Bellman equation will reduce to. And we should remember all these Bellman equations. And also next we describe Bellman optimality equations. Also how to like get those B star and Q star optimality equation. And you should remember these V, Q, pi, P star, Q star, and pi star. How to get these from another. So all those equations were there. You should remember these. And so then you might want to remember this Cauchy sequence and Green's equation. So sometimes, like, in some of the numericals we saw this, we can simply apply this Green's equation. There was an inverse and we were calculating the inverse of the matrix. So you should know how to calculate the inverse of a matrix also. This might be used in some of the MCQs. So maybe like it could be 2 by 2, but who knows? They might give you 3 by 3 matrix also. So you should know how to calculate the inverse, like cofactors, adjoints, are everything. Or if you want to use Gauss-Jordan method, but I think that's long. That will take some time. So I think that's why like they have given you 3 hours. Questions might be still 20 something, but there might be some lengthy calculations. So you should remember that. And finally, like there was this Banach fixed point theorem. So there was a proof of this also. So this basically kind of established that there is a fixed point, and if we keep on applying an operator, then we reach this. So if we apply simply the Bellman operator, then we will reach V pi. If we apply Bellman optimality operator, then we will reach V star. And we also mentioned that although the optimal value functions is unique, there might be multiple optimal policies associated with this. Pi 1 star, pi 2 star, there could be more than one optimal policy. Okay, so also in this lecture, I think we did a demo of value iteration also. So if you have time, you can look into that if you want to understand how these equations work. And then go through the proof of Banach fixed point theorem, and convergence proof was also there of this. And then we move to a week 5. So week 5, we had first topic was L pi convergence. So this operator was there and its convergence was derived that it will converge to fixed point. So, and there was a fact that for finite MDPs, we will always have a deterministic optimal policy. So since we are having a guarantee that deterministic optimal policy is there, we chose not to focus on stochastic policies. So all those small facts you should remember because there might be some true and false kind of questions. And then there was discussion on value iteration, so algorithm. So basically, we keep on applying the operator until it converges. And this algorithm was there. And finally, we had policy iteration. So in policy iteration, we had generalized policy iteration also. And policy iteration is there. So you can look at that policy. This had like two methods, right? Policy evaluation, policy improvement. So first we evaluate some policy, and first then we improve some of the action. And the hope is that by doing this these two repeatedly, we will eventually get to this five star policy evaluation and policy improvement. So you should remember this algorithm policy iteration one, and there was some convergence proofs also, so you should can go through that. And essentially, we discussed something about dynamic programming. So yeah, like planning approaches, they are also known as dynamic programming approaches. So this value iteration, policy iteration, both are dynamic programming approaches. There is one more which uses LP. So basically, they formulate this problem of solving the Bellman equations, Bellman optimality equations as an LP. And you might remember these Bellman equations were linear, right? Equation were linear, but the Bellman optimality equation were non-linear. So if they were linear, then we could have used some simple solving to get the solution. But since there was non-linearity, then we went with this value equation, policy equation kind of methods. Because that non-linearity was causing issue. And there is one more third method. I think this wasn't discussed. So LP, but maybe further you can take it up. Like this LP is also good. Then there was some discussion on asynchronous DP. So you can look at that RTDP, synchronous DP, all those. So there might be small true false kind of questions here and there. So basically, like it was like if you want to use the like current update or just whatever, like for some previous state you have already updated, you use that update or the actual update like which was at previous timestamp. So based on that, you can at that end there was this generalized policy iteration we have already mentioned. So you can look at that also, generalized policy iteration. Then we move to something Monte Carlo methods. So these are sampling based methods. So we basically were generating trajectories and taking the average. Then there were concepts of exploring stars. So you can look at that. And then finally we move to control in using Monte Carlo. And in that also you can see some approximation methods. And eventually like we had this concept of importance sampling. Although this is like not a part of reinforcement learning, but this basically introduced the concept of something called as off policy methods and on policy methods. So essentially through importance sampling, we can do off policy through that importance vector. So you can look at that importance sampling also. There might be some questions on importance sampling also. So you can look at that off policy methods, on policy methods. And in importance sampling also, we saw normalized importance sampling. That also. And finally, like with this, like we kind of finished weeks 5, and in week 5, I think we did demo of policy iteration. And then comes the week 6. So in week 6, we started off with of policy Monte Carlo, and like you should remember these terms, right? Estimation policy and the behavior policy. Behavior policy is what we are using to generate data, and estimation is like what we want to estimate the value or Q values of. So all those importance sampling. Then there was UCT algorithm, upper confidence trees. So you can look at this upper confidence trees also. rollouts, planning, learning, and then finally we went to this TD, temporal difference learning. So there was MC and then finally TD. So essentially in this lecture, I think week 6, we were focusing only on TD0, but eventually it became TD lambda, where lambda takes value between 0 to 1. So TD0 learning, this is like the heart of RL. So you can look at this TD0 temporal difference learning. And there was some discussion on the difference between DP, MC, and TD also. So you can look at that also. I think like this is the last thing. So either like we are at the end. And you should remember that TD update equation, like which is basically the structure of any RL algorithm. So you should remember that TD update equation, like old estimate, new estimate equals to old estimate plus some learning rate times target minus old estimate. So that equation was there. And then TD0 control, in which this update equation will come. And then we discussed the SASA, which is on policy, and Q learning, which is off policy. So you should remember the update equation of the SASA, Q learning, and I'm not sure whether expected SASA was discussed, but you can look at that also, expected SASA. I don't remember exactly. Like I have taken some different RL courses, so I don't remember whether it was discussed in this one. And then finally there was this concept of after state. So you can look at this also. So this is the basic what was done in week till week 6, and from week 7 like we went into eligibility traces, and 3 lectures were on RL, and after that like next over hierarchical RL, and final one is on cognitive. So for that like I'll provide us some the like next lecture on Tuesday. So maybe like do you want me to share this also? So I'll share this also, but there's not much clarity. Okay, so I'll share this also. Okay then. So stop sharing my screen now. Thank you, everyone.
Thank you very much, sir. Have a nice
Yeah,
time,
yeah.
sir. Great session, sir. Bye, sir.
Welcome, welcome. Okay. Now I'll stop the recording.